All right, let's get right into it. We're going to cut through the hype and talk about where AI is making a huge difference right now, every single day. And that's with the kind of data that actually runs our businesses, the structured, tabular data in our databases and spreadsheets. We're going to explore how you build models that don't just win academic competitions, but actually make a difference to the bottom line. So, let me kick things off with a question that honestly gets to the absolute heart of the matter. We're all taught to chase that extra 0.1% of accuracy, right? We tweak and tune to get the highest score possible. But is that really the goal? Is the model at the top of the leaderboard always the best one for the business? And the answer, which might actually surprise you, is a big, resounding no. The most mathematically perfect model is very often not the most valuable one. And understanding exactly why that is, well, that's the secret to unlocking real, tangible business value with AI. This brings us to a new North Star. We have to stop thinking just about accuracy and start thinking about what we'll call business utility. This is the whole shebang. It's not just asking how accurate is the model. It's also asking how much does it cost to deploy and run? Can we actually explain its decisions to a human? And maybe most importantly, is it going to fall apart the second it sees messy, real-world data? This is what we should be optimizing for. So here's how we're going to tackle this. First, we'll lay the foundation with a simple baseline. Then we'll get into the industry-standard power tools. After that, we dive into the messy reality of actual business problems, talk about how to build trust in your model, and finally, take a quick peek at what's coming next. Okay, let's start at the beginning. And this is so important. Every single successful machine learning project doesn't start with some giant, super complex neural network. No. It starts with something incredibly simple, totally transparent, and, frankly, a lot smarter. We always start with a simple linear or logistic regression. And this table shows you why it's so strategic. Yeah, sure, a big gradient-boosted model might squeeze out a bit more accuracy, but look at what you pay for it. It's way slower to train, it's a black box that's hard to explain, and it's a headache to put into production. Your simple linear model gives you a benchmark. It's the score you have to beat, and it's a score you get almost instantly. This brings us to a fantastic concept, the complexity tax. I love this idea. Every little bit of complexity you add to your system comes with a cost, a tax in speed, in explainability, in maintenance. So before you jump to that fancy model, you have to ask yourself, is the tiny bump in performance worth paying that tax? A lot of the time, it just isn't. But what about when it is worth it? What happens when your simple model just isn't cutting it and you really do need more firepower? Well, that's when you turn to the undisputed heavyweight champions of tabular data, the gradient boosting trinity. These three, XGBoost, LightGBM, and CatBoost, are, without a doubt, the gold standard. For structured, tabular data, they just win. But don't think of them as competing with each other. Think of them as a specialized toolkit. XGBoost is your powerful, reliable workhorse. LightGBM is your speed demon, built for gigantic datasets. And CatBoost is your specialist for handling messy data with tons of categories. And the secret to their power is how they build their decision trees internally. It's pretty cool. XGBoost is really methodical. It builds its trees level by level, which makes it super stable. LightGBM, on the other hand, is all about efficiency. It grows leaf by leaf, focusing only on the parts of the tree that give it the most bang for its buck, which is why it's so fast. And then there's CatBoost, which has this amazing secret weapon called ordered boosting. It's a super clever way to handle categorical features that prevents the model from accidentally cheating and learning from the target variable, which is a really common and dangerous trap. Okay, so we've got our baseline, and we've got our power tools. We're ready to go, right? Well, not so fast. Because building a model in a lab is one thing. Solving a messy, real-world business problem is something else entirely. We need to stop thinking about standard metrics and start thinking about reality. This is probably the most critical point to understand. Think about finding credit card fraud. It's a needle in a haystack problem, right? Maybe only 0.1% of all transactions are fraudulent. You could literally build a model that just says not fraud every single time. And guess what? It would be 99.9% accurate. And it would also be 100% worthless. It has zero business utility. And this is a perfect example of how the wrong metric can totally lie to you. That bar on the left, ROCAUC, is a super common metric. And look, it's telling us our model is amazing, a real A+ student. But that metric gets easily fooled by these imbalance problems. The metric on the right, PRAUC, is much more honest. It focuses specifically on how well the model finds the rare positive cases, the needles. And suddenly, our A-plus model looks more like a C-minus. That's the reality check we need. And it gets even more complicated, because your model is going to make mistakes. That's a given. The crucial question isn't if it makes errors, but which kind of errors it makes. Because in business, some mistakes are way, way more expensive than others. So let's imagine we're predicting which customers are about to cancel their subscription. A false positive is when our model wrongly flags a perfectly happy customer, so we freak out and send them a $10 off coupon. The cost of that mistake is $10. A little annoying, but it's not the end of the world. But now think about the other kind of mistake, a false negative. This is when a customer is actually about to leave and our model completely misses it. We do nothing. They churn. And we just lost a customer who was worth $500 to us. That mistake is 50 times more costly. So we absolutely have to build our model to be terrified of making that second, much more expensive error. All right, we're getting close. We've built a powerful model, and we've even optimized it for the real financial costs of the business. But we cannot put this thing into production until we clear two final, absolutely critical hurdles. And they both come down to one word: trust. First, we have to deal with the silent killer of AI projects, data leakage. This is a subtle but deadly trap where your model during training gets a peek at information it will never have access to in the real world. It's like letting a student study for a final exam with the answer key. They'll get a perfect score in practice, of course, but the second you put them in front of the real test, they fail catastrophically. The only way to prevent this is with strict discipline. You have to build a kind of time machine for your data. For any event you're trying to predict, like a purchase, you must guarantee that your model only sees features and data that were known before that event happened. You can't let it peek into the future, not even by a microsecond. This is why things like feature stores are becoming so crucial. The second part of building trust is explainability. I mean, just think about it. If your model denies someone a loan and your response to why is just a shrug, you have a massive problem. You can't trust a black box with decisions that impact people's lives. And that's the whole challenge that explainable AI, or XAI, is trying to solve.
The two big tools we use for this are called SHAP and LIME. Here's a simple way to think about them. LIME is like asking a really smart expert for their best guess as to why the model made a certain decision. It's fast and intuitive. SHAP, on the other hand, is like getting a fully audited financial statement. It's based on rigorous game theory, and it mathematically proves exactly how much each feature contributed to the outcome. So for those high-stakes decisions where you have to know why, you almost always want the audit from SHAP, not just the expert guess.
Okay, so let's wrap all this up by looking ahead. With all the mind-blowing stuff happening with large language models and deep learning, you might be wondering, what's the future for the kind of boring tabular data that runs most companies? And the answer, for today and for the foreseeable future, is actually really clear. The gradient boosting decision trees we've been talking about this whole time are still the undisputed kings of this domain. Yes, deep learning is making some fascinating progress, but for the vast majority of real-world business problems, GBDT still hit that perfect sweet spot of performance, speed, and efficiency. They are not going anywhere anytime soon. So I'll leave you with this final question to really think about. If your AI model's predictions have a direct, real-dollar impact on your company's bottom line, you have to ask yourself, are you optimizing for the right thing? Are you just chasing a leaderboard score? Or are you truly optimizing for business utility? Because answering that question, well, that's the difference between building a science project and building a true strategic asset.